Okay, well, thank you for asking me to come over. I give probably in the last, since Katrina, I think I've given 200 talks about this sort of thing. And people are always asking about, you know, can our coast be saved? And I'm basically I'm a scientist. I'm actually a geologist. I care about why things happen. And as far as this question, can the coast be saved? I don't care. Okay, I don't live in the coast. I don't care, because if you care, then what creeps in, I think, in a lot of cases, is that people begin to substitute objectivity, or they substitute agendas for objectivity. I learned a long time ago that even though I do politics all of the time, I spend most of my time talking to politicians. And I've learned, don't try to out-politic a Louisiana politician. It's not going to work. They know they have different ideas. I understand the political process and where this fits in. So my objective is basically to tell the truth. Okay, whatever that is. In other words, I'm trying to give people a sense of what the reality is. What they do with it that's up to the people of Louisiana to deal with. Because there are many more things than science. Hopefully we don't live in a society that is governed by science. That would be the worst thing you could have. What you want to do, this is a pluralistic society, and there's a lot of different issues, and people have to make choices and decisions. I will say straight up that South Louisiana is a really stupid place to live, geologically. However, I grew up in Los Angeles. There's a brilliant place to live, sitting right next to, a fault that is going to move and knock down half of the city. Or people who live in Seattle, you have an active volcano right behind you to the east. You've got a magnitude 8 earthquake right around the corner. The bottom line is, every place has issues. The question is, do you know what your environment really is, and how are you going to prepare for it? And if you prepare for it, you can deal with it. If you don't prepare for it, nature will take you out. Period. End of conversation. And so let's just get at that. I'll be pleased that people can actually understand and deal with the reality of what's happening in the coast. The takeaways from this talk are basically that, and it's not so new data, it's just that someone or groups of people have finally decided to look at the full spectrum of data and trying to understand it. What it basically says is that the scientific paradigm that governs policy in this state is wrong. They got the geology wrong. We can discuss why that is and all of that, but I'm going to try not to do too much of that today. Politicians have accepted this false diagnosis, and public policy has been developed to save the coast. However, it'll fail. It's not a wetlands problem. The state spends, I don't know how many millions of dollars on PR pumping up, the wetlands. Hell, they've got action figures. I don't have action figures. They got coloring books. I don't have coloring books. So, but the good news is that lawyers are ultimately going to decide what goes on, because this is going to be such a mess in so many different ways. It's going to wind up in a court, and some judge is going to decide. Probably it'll lead to such, nature will basically get tired of it and deal with it. So can we save the coast? I have to come back to the question, save it from what? Nature? I mean, what we're seeing on the Louisiana coast in many ways is quite natural. You've heard that it's the big bad evil oil companies that are to blame. there's no question oil companies have done horrible, awful things to the coast and are deserving of some proportion of the blame. But let's use a medical analogy. I mean, the previous diagnosis, the people that are actually paying for it have decided that they're convinced of what's going on, and they're charging ahead, paying for the treatment. I think we've spent, the BRO Act is, I don't know how many billions of dollars, probably close to $1 billion on coastal restoration. You know how many of those projects have worked? I think there's been like 200 projects. You know how many have worked? One. Gee, isn't that surprising? Shouldn't we expect at least some accountability in terms of whether these things work or not? If they don't work, I have an old-fashioned business model. Find something that works, do more of it. If it doesn't work, stop doing it. I'm naive. You told me that before. So the specialists have told everybody what the treatment is, and all of these things have failed. We've got independent tests. See, in science is never over. Science is never over. All science ultimately is shown to be incorrect, mainly through the fact that we're able to observe in more detail, and we begin to see how the world works at different scales and more complexity. The world is complicated. The problem here is the insurance company, in other words, the federal government. They haven't changed their stance. Right now, they're talking about, we're going to restore the coast because of the oils. You've read it all. The problem is that the insurance company will not change its view, and it continues to pay the podiatrist working on the problem. The problem is the patient's dead, and they find out it was a brain tumor. In other words, they've had the wrong specialists looking at the problem. These types of issues, very complex environmental problems, are often so multifaceted. You can't expect one thematic group of scientists to be able to look at it. Where do we see the most obvious degradation of the Louisiana coast? Where? The wetlands. Okay. Where's the disease? Must be the wetlands. So you focus your efforts in the wetlands, and people study the wetlands. There were geologists that figured out how the coast works about 150 years ago. But because of the focus on the wetlands, they forgot to continue to look at the rest of it. And that's the problem. Anytime you, I remember my advisor, my PhD advisor said, when you're ripe, you're rotten. In other words, when you think you understand something, you're in trouble. Don't ever get to that point. Continue looking. Just because you found something, doesn't mean that you shouldn't continue to ask, do I really know this? What do we really know? Well, what's happened? What are the symptoms? The coast is going away. The coast is eroding. Canals have been dug into the wetlands. Levees and dams have starved the wetlands of sediments, nutrients, and water. Blah, blah, blah. You've heard the whole thing. Wetlands are turning into open water. We know this. What else? Recent tropical storms have really ripped the scab off and have shown us what the vulnerabilities are. And we ask the question, why is this? Is it global warming? Is it weather changes? Land changes, sea changes. Is the land going down? Is the water going up? What the hell is happening? You see all of these red lines. These are the tracks of hurricanes, tropical storms for the last 150 years, 160 years. And so this is a vulnerable place. Without thinking about anything, there's a lot of these storms that come around. Here's the frequency diagram of hurricanes for the last 110 years. And if you see a trend in here, I don't know, you might. Is there something happening? Could be. There's the average. We've had some. It looks like the problem with the averages is that just think about a drunk walking down the middle of a two-lane highway, walking along the line, dividing the lanes. On average, he's in the middle and he's safe. The problem is the variance. The variance always gets you. So we see this above average. Okay, here is the Atlantic multi-decadal oscillation. In other words, there's patterns in the climate, and we're probably right now on the near the maximum. We've seen a lot of storms lately. Over time, I suspect in your lifetimes, as you become law professors or partners at fancy law firms or chancellors in the future, you'll see you'll be in the good times. Here's the part of the bottom line here is that here this is a topographic profile. In other words, the elevations of the land from basically Baton Rouge down to Belchase or something like that. And you see this. There's not a lot of room for error here. The topography is quite low, and the elevation of sea level is not zero, believe it or not. It wasn't 50 years ago. We thought sea level was the same elevation everywhere. As it turns out, sea level, there's a variation of several hundred feet in sea levels around the world because sea level is determined by the Earth's gravitational field, and the Earth's gravitational field is not uniform. But we didn't have the technology to see that. But you see, it gets pretty low here. Here's the Baton Rouge Fault. Here's North Baton Rouge. This is actually just north of the lake here. And then down here, that's on the south side of the Baton Rouge Fault. And you see some high areas, and you see levees as we cut across the Mississippi. You see river levees. Here are the man-made levees. Here are the natural levees of the Mississippi River. And we've augmented them to keep the water from flooding. So this is a vulnerable place. You make a mistake of inches, you're going to pay for it. The prevailing, and this is probably too much detail, but the prevailing paradigm essentially says that the coast of Louisiana is fairly stable. What our measurements show is that the Louisiana's coast is quite dynamic, and that's the key here: dynamic versus stable. The scientific paradigm basically claims this stability, and only the wetlands are changing. Well, the wetlands certainly are changing, and we see the effect here. You see in this underlying picture here, this is shows all of the canals. This is down in Terrebonne Parish, I think. And you can see where evil oil companies have come in and dug canals and have torn up everything. No one can deny this. And the reasons for this change have been that building river levees starved the wetlands of sediment and fresh water. The Mississippi Delta is composed of dirt derived from the Rocky Mountains, plus the mulch developed by the organic soils and sediments that were developed through the canal dredging. You dig all these canals. That is, you're basically encouraging salt water to flow into marshes that are not salt tolerant, and they die. Areas get. We all know that is something that happens. Sea level rise. We know that happens. Subsidence. Well, we know subsidence is occurring. But most people think it's due to natural processes of compaction and recent sediments. People think oil and gas extraction is a big factor. Water pumping, this is huge in Houston. But in Louisiana, no one's really talked about that very much. And levees and drainage projects. When you build a levee to protect yourself, you make yourself more vulnerable in many ways. It's all true, plus erosion. It's all true. That's the problem. It's all true. You know, how many people have been executed in the United States because all of the evidence pointed to them, except the DNA that finally somebody found. You see, there's never enough. Never trust it. Always look for more. Always verify. That's what scientists do. That's not what engineers do. I'm a professor of civil engineering, so understand, I have to go home. So you will hear interesting things. So the big question is where's the land in relationship to the Gulf of Mexico? The Gulf of Mexico is our enemy. No one will be killed by subsidence unless you really have some potential for the Darwin Award. If you come close in the past to getting the Darwin Award, you'll be killed by subsidence. No, the vulnerability will get you. The storm surges, taking advantage of the vulnerability will kill you. It won't be the subsidence. And so all of these questions, is it the land changing? Is it going down? Is the sea going up? Or is it both? Well, obviously sea level's rising. Here's a sea level curve history from since the last glacial maximum about 18,000 years ago. Well, as soon as the glaciers started to melt, they melted pretty darn fast, and sea level began to rise. Sea level offshore Louisiana, sea level off of the Louisiana coast used to be 400 feet lower than it is today. Think about that. Well, that kind of explains why the bottom of the Mississippi River out here is at minus 60 to minus 80 feet below sea level. You know, how'd that happen? Well, river's down cut, depending upon where sea level is. Sea level rises, the river will then choke up with sediments. You drop sea level, and it will begin to fall. The Colorado River, anybody rafted on the Colorado River? Okay, where did the Grand Canyon come from? It's because the Colorado Plateau is rising, and the Colorado River sits there like a hot butter knife cutting down through it. And so you change these things, the world responds. But about 4,000 years ago, 5,000 years ago, sea level began to slow down. Sea level rise began to slow down, and we were in this situation here. Well, remember I said that as sea levels began to stabilize, the Mississippi River and all of the debris that comes out of it started piling up on the coast. Before, it was just shooting out into the deep ocean. And now it's beginning to back up and fill up. And over the last 4,000 or 5,000 years, the Mississippi River has basically the Mississippi River Delta has been able to maintain itself relative to sea level. Deltas never build themselves very high. They can't. The river doesn't flow uphill. The river, as soon as the things pile up enough, the river will switch and start piling up over here. That's the history of the Mississippi River Delta. Well, what's happened? What's changed? Well, here's sea level over the last 100 years. The cool part about sea level in the 20th century is that we actually have observations. This is not, and they're really good observations from tide gauges. And what do we see? Well, what do we typically do as scientists? We see a bunch of data here, and then what do? We go over here and we run a regression line through it. And it turns out to be about 2 millimeters per year. It's about a credit card every year. 2 millimeters in 100 years is how many feet? I know you're lawyers, but you can do math. I know you can. It's about 8 inches. Okay, 8 inches. Not a lot. We can deal with that. The question is, what do we find embedded in this? Whenever you take an average of something, what happens? You give up something. You give up an understanding of the details. What's some of the details? Let me tell you about some of the details. There's one over here called Camille, another one over here called Betsy and Katrina. And those particular, those departures from the norm are the things that you have to worry about. So don't, the averages are nice, but understand that you have to understand sea level rise. You have to, especially for living on the coast, you have to understand the total fidelity of it. You have to understand the details. Unfortunately, we plan using these averages in many ways. Let's look around the Gulf of Mexico. Pensacola, 2 millimeters per year. Hey, what does that tell you? Hey, Pensacola's stable, pretty much, with respect to sea level. Geologically, it's not moving around too much. On the other hand, Eugene Island, which is down, south of New Iberia, 9.6 millimeters per year. Sea level was 2 millimeters a year. Subtract 1 from the other. It's about 7 millimeters per year. That's more than 1/4 of an inch per year of subsidence there. Grand Isle, Louisiana, same kind of thing. In other words, it's not sea level. So we've seen that there's more than just sea levels rising causing the inundation of Louisiana. There's something else. The land up here, the hypothesis that I would come up with is that land is sinking. Here's the details again. This is over at Galveston. This is along the entire coast. The area of subsidence actually goes all the way from about near the Mexican border, probably Corpus Christi, all the way over to Pensacola. This area is sinking, and then you have the combined effects of sea level rise plus this. And who knows what sea level rise is going to be in the future. I don't even want to go there. This is an interesting picture. This is another way of looking at change. This is a map, and if you can probably see this better than I, but you see there's a stipple pattern of areas. But you see underneath it some other colors. Well, the stipple pattern shows you where the coast was in 1932, according to NOAA. This is the official coastline of the United States. I've draped this over a modern air photo. And what you see is change. Well, I will agree with you. This is a very difficult way to assess the amount of subsidence and things like that, because it all depends on at what time of day did you take your air photograph. However, yes. Well, it's the lighting. Pardon me? Yeah, the red is the. Let's take this over here. Here's an island. This is over near Grand Isle. This would be maybe Belterre or something like that. And you can see in the red is this is a false color, so that's vegetation. So you're seeing the land. Here you can see actual beach over here, but here you see these outlines with nothing under them. This stuff's gone. That's right. Or that it's been eroded, or it's just not there. But you see in a lot of areas, if you look very closely, you see that the stuff that's remaining is this big. If you look at where it was like this. And so one explanation is that the water has gone up. It's kind of like a pyramid. Think about a pyramid, dunking it in some water, and then filling it up, you'll see that the footprint changes. Well, we have public policy that governs all of this. They spend $6 million, keeping some of Mr. Bill's characters out there and talking to kids and everything else. And I'm sure how many years ago it was just actually last year where they stopped doing this, where at the end of the holidays, if you had a Christmas tree, you put it out on the curb, and they took the Christmas tree and they used it to save the wetlands, right? Save those wetlands. They didn't do a damn thing. It's not going to do a damn thing. On the other hand, people asked me, one of the governor's people asked me, should we keep doing it? And I said, hell yes. It's good that people think that they can make a difference. However, it doesn't do a damn thing. So, you reap what you sow. What are we going to do? Restore the wetlands? It's not working. It doesn't work. It won't work. You'll get a short-term something, but then it'll be gone. Anybody following the sand berm business? Let's build some sand berms. Anybody ever done, as a child, gone out and built a sand castle? And how disappointed you were the next day when the sand castle was gone? Well, Louisiana lives in the tide zone, so to speak. And so anything that you put there, nature is likely to take away. How about building the Great Wall of Louisiana? I get a lot of grief from this because about 4 years ago, there was a Modern Marvels. I guess that's what it was. And I was interviewed on this thing for the program, and the producer was such an asshole, such a jerk that he at the end of the day, I was very pissed off, and he was ready to storm away. And I said, well, I didn't tell you about the Great Wall of Louisiana, did I? And he goes, whoa, hey, I want to hear about that. And so the idea of building a big giant levee system around Louisiana to protect it. Sure, it'll protect it, but what are the unintended consequences of doing things? The problem with nature is, and this is the problem with engineers, is that they solve problems, but in the process, what will happen later on? How will you deal with the implications, the changes that are caused by that? Retreat from the coast. You're never going to get a politician in South Louisiana who's going to say, hey, let's leave. Wrong. It's not going to happen. So they'll never be that they can't lead. Nixon went to China. Okay? Because he could do that. He could make that change because he was one of the hardliners against China. Same thing here. Politicians on the coast aren't going to say anything. In North Louisiana, hell, they don't care about South Louisiana. Polter the coast. In other words, a Holland-style plastic surgery of the coast. My guess is this is where we're going. Turn it into Disney World. I was in the Netherlands a couple of weeks ago, and when I landed, my wife looked out and said, oh, look at how beautiful it is. Look at how well organized everything is. And I said, yeah, it's freaking Disneyland. There's no nature there. What do they want? What do people want when they say restore the coast? They want to restore the ecology. I hate to tell you this, but South Louisiana, it's invasive species. There's very little that is natural anymore. The entire region has been altered. The hydrology has been altered. The land use has been altered. They do things down there that you shouldn't be doing. Now you want to restore it to what? My guess is this is the solution, because this is something that they can do. And I deal with these. You don't want to play poker with these people. I think there's a secret plan. I think that that's what they want to do. But they're not going to say anything because the implications. All right. Well, why is this? Well, what I've noticed is that the mentality of science in the coast is really that of an engineer. Engineers are different than scientists. Engineers design solutions that to problems that people pose them. And they determine, what's done is you ask the client or whoever it is, what's your outcome? What do you want? And they try to do that depending upon how much money you have, how much time you have. And they follow and this is probably the most important thing I'm going to say, they follow the doctrine of the best available. We use the best available data. You've heard this, right? We use the best available data. Imagine you're in a foreign country and your car turns over and the doctor says, I'm sorry, you're going to have surgery. And you say, well, okay, go ahead. And he says, well, our autoclave for sterilizing all of the equipment, it's not been working too well. So we used the best available. There's kind of an open sewer out here, and we kind of rinse things off over there. It's the best available. Plus, we have to use blood. We're getting blood from the monkey research lab down the street. It's the best available. No, best available is not good enough when you're dealing with lives and property. Engineers need to change this. And they use the best available science. Come on. There is no such thing. This is expediency because engineers actually have to do something. Scientists don't have to do anything. I can just sit on my ass and I can say, I don't have enough data to make any conclusions. Engineer actually has to do something. It's a fundamental difference. However, the way that we deal with science in this state, it's done with an engineering mentality. I go to these meetings and they talk about, well, we're here to develop some scientific consensus. Hey, this is like crying in baseball. There ain't no crying in baseball and there ain't no consensus in science. It's either it is or it isn't or you don't know. But engineers have to do something. Scientists try to figure out how the world works. We're accountable only to other scientists. We don't have to do it like engineers. Engineers have to do something. We are governed by sufficiently and accurate and precise to test hypotheses that are at hand doctrine. If I went to a meeting of oil finders, and I said, I have developed a hypothesis, and I find oil 35% of the time when I look in new areas, I would be hailed. I would be carried out as the conquering hero. If I go to the American Geophysical Union or the Geological Society of America and I say, well, my model, I can explain 35% of the data, they would laugh me out of the frickin' room. And so, there's different standards of how we do things. There is no consensus. However, people continually talk about, well, the consensus is, no, there's no consensus. Just admit, we're really not sure of what's going on, but we think this is the best guess, and we're going to give that to the engineers. And that's what they do. And the success is defined by how well can you explain old data and also predict new data that you might collect. The problem is engineers are going to be the people that are going to fix the coast. It's not going to be scientists, it's going to be engineers. And that means they're going to design hurricane protection systems. They're going to, whatever we ultimately do to the coast, to the wetlands or whatever, they're going to move dirt. They're going to have pipelines, they're going to do this, or they're going to dredge and whatever. The bottom line, they're going to do it. And it's going to be private industry that's going to do it. What they're interested in is design of flood protection that is going to last 50 to 100 years. That's the design life of most engineering projects. And how do we do this? We basically use very sophisticated, or not so sophisticated, numerical models to make predictions about how bad could it get? How high can the water get? And so for after Katrina, they basically have to say, okay, how big can it get? There's a lot of controversy about that, but ultimately, I said, oh, we got to build a Category 5 hurricane protection. Well, Category 5 hurricane protection doesn't tell you anything about surge. Hurricane Andrew, back probably when you were you were very small, and we were smaller. We basically, when it went through Florida and destroyed the Homestead area just near Miami, it was effectively a 5-mile wide tornado. That's what it was. On the other hand, there are some Category 5 hurricanes that are huge. They have wind fields that are hundreds of miles of hurricane force winds. And so this is a misnomer, but this is the politics of it, and this and that and the other thing. But ultimately, they come up with some sort of, how about Katrina? Katrina it was a glancing blow to New Orleans. That isn't anywhere near close to how big it could get. If there was ever a Category 5 hurricane that there was a direct hit on New Orleans, you wouldn't have anything left, because there's no Category 5 roofs in New Orleans. That's the thing that we're always focusing on surge. But the fact is, it's wind. And the homes that we have in much of South Louisiana are not good enough to stand up to such things. One of the most important things to start with is knowing what is today, so we can have a starting point to do our modeling, the present-day topography. And what's the future landscape going to look like? We want to run a storm surge model in 50 years. What's the topography going to look like? We know that New Orleans is below sea level. Was it always below sea level? No. A lot of people think that's the case. But what do you have in Louisiana if you have an area that's below sea level? Let's say you go dig a hole in your backyard tomorrow. What are you going to find the next day? You're going to find a lake. There's no areas that are naturally below. This is not Death Valley around here. This area is going to fill up with water, and there are lakes. And so the subsidence that you see in New Orleans, the areas that are 15 feet below sea level, those are the result of human activities and the way that we respond. Sometimes there are unintended consequences that make us more vulnerable. We have to balance the good things with the bad. Okay. Risk analysis. Skip over this. Well, maybe we can't. Yes. All right. How far? We're going to try to figure out what the future is going to hold. Well, how do we do that? Probably a good idea is to kind of look back. Now, how far do you look back? You want to look back a million years? A billion years? Is a billion years going to tell us anything about what's going to happen? Probably not. And so there has to be some sort of decision and an analysis as to how far we should look back. Personally, I think we need to go back and look at least 100 years. That makes sense. Because much of what we have in the coast is human created. So the geological record, the long-term history of the Gulf of Mexico is very useful. However, one of the biggest geological agent, wind is a geological agent, running water is a geological agent, human beings are geological agents. They cause things to happen. So we have to understand these things. So to understand the causes of the risk, you have to understand what's going on. And the first step in understanding any kind of science is you got to measure something. That's what science is about. You measure something, and then you compare it to what your models that you've developed, either first principles or empirical models, and you see whether the models are predictive or not. Let's review how the coast works. Here's the Louisiana coast. Here is Lake Pontchartrain. Here's Plaquemines Parish. This is southeastern Louisiana. How did it form? Well, it's the modern Mississippi River. Basically, is fairly new. This was open water before. It's real simple as to how this place works. It's the interplay between subsidence which is the lowering of the land, accretion, sediments piling up, ocean processes, waves that are attacking the coast, eroding it away, and global sea level rise. If you can figure out those things, you can figure out what the landscape is going to do in general. Flooding is an essential part of the creation of this area. The Mississippi River, every year or so, would break through its banks and then flood areas. Fundamental. It's fundamental to the ecosystem, fundamental to the geological system here. Every once in a while, every 2,000–3,000 years, the Mississippi River would pile up enough stuff that the river says, you know, it all operates on the basis of energy anyway, and it said, well, let's just start dumping sediments over here, or over here, or over here. And it would do that. During those time periods when these are called sediment lobes, these things are being fed, and the flooding would occur here. This would be the healthy part over here. The areas that were abandoned would be slowly dying because they're not getting flooded anymore. Flooding is an essential part of a delta. Over time, the deltas eventually subside because they're not building up, keeping pace. They're compacting. There are other factors going on, and ultimately it drops below sea level. Waves are attacking it, winnowing away the fine material, shoving it out onto the shelf, leaving behind barrier islands, things that we call barrier islands. Barrier islands, when you see barrier islands on the coast of a delta, it tells you, those are the tombstones of the delta. It tells you you're finished. It's not like the barrier islands along the east coast, which are fed by rivers and things like that. The sediment from the barrier islands that we have are all due to that's the residuum. It's what's left over after the waves attack everything. They leave behind the big stuff, and that's the barrier island. Well, one of the things that I do as a geologist, geophysicist, is I'm interested in understanding the mechanics of why this happens. Well, this is a scientific word. It's a big pile of goo that sits over here, and it's like standing on a diving board. The Earth does not have infinite strength, and so whenever if you stand on a diving board, it bends. Okay, and the bending occurs not just under your feet, but it distributes the deformation out along the diving board. That's what happened here. This big pile of goo is enough to push down the Earth's crust, also the Earth's mantle underneath. And it's actually made the Earth's mantle flow. It's hard to believe, but it does flow. In fact, since the last ice age, you know, that big pile of ice that was sitting on top of Hudson Bay, that stuff melted. Well, that ice had actually pushed down the crust, pushed the Earth's mantle down towards Louisiana. Well, when it melted, it's flowing back. You know, it's hard enough to get some of these Cajuns down on the coast to understand this basic principle, but when I start talking to them about that subsidence is partly due to the flow of the mantle back to Hudson Bay, that it probably results in maybe 1/10 of a millimeter of subsidence every year. It's a little hard to take. Well, here's the problem. Human beings from Europe move into this area, and they start trying to live in this area. It's a beautiful place. Fishing is unbelievable. Trapping, it's unbelievable. But, you know, these floods, every year these floods are annoying. And you try to build a society with flooding. People said, we don't want to flood it anymore. So what did? They came over to the Mississippi River, and they built river levees. And it has stopped the flooding. We haven't had a major flood in this region from the river for, close to 90 years. It worked. Fantastic. Engineers did their job. The problem is, what have you done? You've disrupted the natural system. And now this area that relied on flooding to keep pace with the subsidence doesn't happen anymore. You've disrupted this natural environment, and now you're going to pay the price for it. And the price is we're losing the coast. The proximal cause of the loss of the Louisiana coast is the Congress of the United States building Mississippi River levees. That is the number one cause. That is indisputable. Ask any coastal scientist, that's what they will tell you. Even if there was no oil companies doing anything to the coast, we'd still have these problems. Yes. Yes, sure. Well, as it sinks, you replenish the elevation that you lose with more stuff out of the river and that sort of thing. And the marshes would be healthier and everything else. The problem is what? You can't live there. And so people can't, you can't farm there, you can't do anything, and people said stop the flooding. See, if you would have, it's all about lifestyle, choices. You go for one choice, you know, there may be something bad behind door number one. On the other hand, it achieved everything, but the problem is it took a while for the effects to show up. Okay? So it comes down to this. Balance is required for, you know, we hear about this sustainable coast. Well, it all comes down to this very simple balance of equation. Sediment accretion, things building up, balanced against the factors that are essentially leading to inundation. Global sea level rise, regional effects of, you know, waves and currents. This is probably nothing to worry about. Subsidence, the land sinking. So you've got to be able to have enough sediment being piled in. This is exactly what you were asking. Sediment accretion has to, if you want balance, that's what you got to do. So why is the coast being lost? For the most part, it's because this doesn't happen anymore. It's severely curtailed. Global sea level rise doesn't care. We can't affect that. And subsidence. We can't affect some of the processes that are causing subsidence. There are some things that are man-induced, and we can do something about that. But we don't do anything about that. And so if you're going to solve the problem, you have to solve this equation, but the fundamental is you don't have anything building it up. The other problem is, where do these sediments come from? They come from the river. They say, open the river. We're going to do diversions. Fantastic. Let's mimic natural processes. Makes sense? Nature knew how to do it. Problem is, upstream on the Mississippi River, what do you run into? If you wanted to take a power boat, a cigarette boat, with all the gas and start and going to the end of the Mississippi and Missouri River, what do you run into? Dams. Damn right. Okay. What else do you run into? Well, the fact is, a lot of the sediments that were coming down the river don't flow down the river anymore. Why? Because soil erosion practices. We're better at keeping the soil on the land. We allow runoff and all of the liquids that are filled with nutrients that ultimately come down here and cause algal blooms in the dead zone and all of this other stuff. But the sediments are being shut off. You're going to have to go back and tell everybody in the TVA that you're going to knock down all the dams, but even if you did that, you still wouldn't have enough sediment to fix the delta. There's not enough sediment. There's a lot of, you know, people can question how much and this and that and the other thing. The fact is, there's certainly not enough. If you've got really high rates of sea level rise, there is no way it's going to happen. So the big question is, how is sea level changing along the coast? And how will it change over the next 100 years? How does one study sea level and subsidence? what's the best strategy for understanding what we call relative sea level rise? This is relative sea level rise, means that's effectively the subsidence plus the global sea level rise. Well, what is subsidence? Well, got to get your terms down. It's downward movement of the surface of the Earth with respect to a datum, a reference. Problem is, I'm a geologist. Geologists don't do things with references. The other side of me is the measurement guy, and over the years, a part of the geophysics is that something that we call geodesy. Geodesy, the practical use of geodesy is surveying. Geodesy is the study of the Earth. It's the mathematical description of the figure and shape of the Earth, and that's very geophysical, very mathematical. And so, in what I've been able to do is to take geodesy and apply it to geology, so we can actually do measurements to actually see how things are actually happening. We're not going to do it the geological way, which basically takes stuff that you can find that may be thousands of years old, and then extrapolating it to the future by some sort of very simple-minded regression or something like that. The problem is the Earth's surface is almost impossible to measure through time because it changes. The Earth moves in unbelievable ways. The Earth heaves and it rises and falls just due to whether it's rained or not. It'll puff up the clays. You know, in this area, you know, off of Highland Road, those areas are very nasty places to live because of the fact that the clays are there and they tend to create foundation failures. So be very careful if you buy houses. Come and ask me. I'll be happy to help you. It'll be a small fee, but I think we're friends and we can do that. So what does subsidence look like? I'm sure you've all heard about subsidence. What does it look like? Well, it kind of looks like this. This is a nice little home in New Orleans East. But what do you see? What strikes you about this? Well, it's a ranch-style home. You know, it may be gauche. It may be out of style, but it's there. But what I notice is the very broad and welcoming sidewalk up to the house. Have you noticed that? It's very welcoming. But then I look back over here and I see this looks very strange. What is this? Well, that's the old garage. This is actually a driveway. And people have converted their driveways or their garages into bedrooms. Why? Well, we'll talk about that. Here's another one. You know, yeah, the driveway is just built on the natural ground, and it's subsiding like crazy. The house is on piers, and so it doesn't subside as much. And so you're seeing differential subsidence, but I don't know, maybe this looks like some two-lane engineers. That's what I'm thinking. Yes, sir. Well, LSU sits partially on the floodplain of the Mississippi River. If you notice, Highland Road, that's high, old. When I first came to LSU, I bought my house up there. Why? I'm a geologist. I can't be seen flooding. This is a bad thing. So the last time this area has flooded, where we are right now, is about 13,000 years ago. On the other hand, you go down to Gardere, South Campus. These are places that flooded routinely before 1927. Okay, and so there's more to construction and foundations than just the local subsidence. It's the clays and the expansive soils and all of that. But notice this. I mean, they obviously didn't. You know, you can't get into the driveway anymore. You drive up and you high center and you're finished. Well, here's another place. This is a place that's abandoned after Katrina. But here you can see underneath. The house is still on piers. It's just that the ground has moved away from it. And you see this throughout New Orleans, you know, in Metairie and areas like this, where a lot of people would spend their summers shoveling sand underneath the houses and built them up. If you go around and look, you'll see this very thing. But this is the so this is the typical kind of, this is what most people think of subsidence. The problem is this house sits on piers. If you put a GPS antenna like we have, the GPS that I have costs about $30,000, and I can measure changes over 5 years of a couple of credit cards worth of displacement. What this shows is this house is actually subsiding about a half an inch per year. Out here it's a half an inch a year plus whatever this amount is in here. Okay, so subsidence is not always something that you can see. There's deep subsidence and shallow subsidence. Well, here's a good example. How many people here from New Orleans? Okay, the Green Bridge or the Parish Road Bridge. You know where this place is? Okay, it's okay. You'll get over it. No, that's a joke. There's a water gauge stuck on the Green Bridge on the Parish Road Bridge, and it's been recording the daily at 8 o'clock in the morning. A little man would come out of the house and he'd look at the gauge and he'd write it down. And they do this at a bunch of these gauges in New Orleans, and this is the history of it. And what you see is early on, until about 1960, it was subsiding at about 7 to 9 millimeters per year. Then suddenly, boom, it starts subsiding like crazy over here, and it's done so for the last 50 years. Well, as it turns out, and I'll explain this later, what sits, the Green Bridge, the foundation there, this is on the New Orleans east side. What's over there? There's a power plant. Okay, it's Entergy plant, and there are huge water wells right there. And this area has subsided several feet. You're not supposed to build interstate bridges that subside, you know, 2 or 3 feet. But that's what happened here. But it also lowered the land. Well, that's the Mr. Go area, isn't it? As it turns out, this particular area was one of the few places where there was overtopping during Hurricane Katrina. The other part, there is an area that they're trying to do some coastal restoration, Bayou Bienvenue. The area is subsiding due to these water wells over here in that area at a rate there is no way the marsh could keep up. Unfortunately, the fellow that was here last week doesn't know this. And so when they go out and try to do this restoration, it will never work because the marsh can't keep up. Marsh can't grow at rates of several feet per year. All right. So, well, I'm going to jump through all of these, the measurements. Basically, where I come from in this is you got to measure things properly. The way that we've been doing the measurements have been crude. What we're talking about here is millimeter scale measurements using high technology, proven technology. But here's the probably the big deal here. You see these two examples here: a calendar and a stopwatch. They both measure time, don't they? However, the choice of the tool that you use to measure things must be appropriate to what you're trying to measure. You would agree.
This time they're away, and what an opportunity for one of these men. It's pretty even at the moment. Curly going well. Lamont Jacobs on the far side. And the Italian.
Now, which one of these things would you use? Obviously, you could use the calendar, but the calendar doesn't give you the resolution to figure out who won, does it? Stopwatch does. So if you're trying to measure the process, you have to use a tool to capture the process. The problem with the way that people have been measuring subsidence is that it was too crude to actually figure out how much of the signal was caused by this process as opposed to this process as opposed to this process. And we've come up with an average which is smoothed over, the mean smooths over all of the outliers, all of the other things, the natural variability that is built in that we see in the observations. All right, we've measurement. You heard me talking about measurement. So the misunderstandings about the coast are really fundamentally rooted in this, and until people wake up to this fact, they will never then come to the next conclusion as to what the processes are. So the difference between the stopwatch and the calendar is the sensitivity. And as it turns out, the differences in the methods that were used, the geodetic measurements as opposed to the geological measurements, is 1,000 times. Or 40,000 times. What do I know? So here's what we see today. They think that subsidence is very stable. It doesn't occur. That's because they're averaging over huge amounts of time. Here's some of the data that's used. Look at these are individual measurements, and they do all of these measurements as the idea is that as sea level rises, it produces deposits that are subsequently buried as you go along. And if we can go out there and get this thing and date it and then plot it on this, we can come up with a relative sea level rise curve. Make sense, right? If you're a geologist, this is understandable. However, what are the errors? Look at how big the errors are. Huge. And we're talking about, this is 3,000, 2,000, 1,000 years, 500 years. We're talking about this. We're trying to understand what's going to happen over here the next 100 years based on what's been happening on average for the last several thousand years. That's what we've been doing. And there's so many other things that go into this that basically makes this kind of an approach for this kind of problem untenable. The problem is, a lot of people have built their entire scientific careers on these things. They're not real. Hey, attention everybody, God, I screwed up for the last 30 years. It's not going to happen. And so what is happening, though, is that people begin to see what's happening, and those ideas are being shoved to the side. That's the way science works. Science works by ignoring stuff that doesn't work, and it moves on, follows the path. All right. We've talked about long-term averaging. I'll try to get through this. But fundamentally, the paradigm thinks that the coast is stable. Fact is, it's not stable. Well, working in parallel, suddenly the surveyors in Louisiana have been always perplexed by the fact that the benchmark elevations that they use to figure out where the flood map is, or where the flood zones are, and to build the levees high enough, were changing. In New Orleans, they would build projects that wound up this. A benchmark is typically it's a piece of brass, or it's essentially some sort of a mark that is put out by the surveying community to represent points of known elevation or position. And people used to spend a lot of time kind of figuring out where these things were. It was quite complicated, quite involved. And over time, though, it gets to be more and more expensive to do. So in New Orleans, when they built project, they built this one levee up to over here, and they said, well, it's supposed to be at plus 15. Well, they would build it up here, then they would come back later, the next year, or 20 years. The ground had subsided, the benchmarks had subsided, but they still thought the benchmark was at some previous elevation. They would start there, and they would then build that, and they would wind up with the new levee up here and the old one over here. They were supposed to be built to the same elevation. The problem is the benchmarks had changed. So in the process, finally the United States Congress asked the federal agency responsible for this to tell Louisiana how good that system is in Louisiana, and they said it's inaccurate, obsolete, and unable to support public safety, and this was in 2001. Well, they didn't get around to fixing it until they funded us, starting in 2002, to get it together, and the system was fixed after Katrina. And what they did something very amazing. They basically threw out all of the old data and replaced it with a fraction of the new correct data. The problem is most of the surveyors in Louisiana were not able to handle this. Suddenly, undoubtedly, the flood certificates that you have on your homes were not done correctly. The flood maps were not mapped properly. Today, FEMA has now figured this out for the entire country, that everything is so screwed up. They've said, hell, we don't know where anything is. We're decertifying levees. We're redoing all of the flood maps, and people are getting hurt. The new D-firms are based on new topography that was done in digital. Those maps were based on faulty data, and we've shown this to FEMA, and what do they come back and say? We use the best available data. Now, is it right? It doesn't work. They are demonstrably not correct, and they have not followed in the construction of these D-firms. They did not even follow their own guidelines. However, we're FEMA, and you're not. So we were funded to fix this problem, so we've gotten a bunch of money since then to work on this. We've now basically come up with a 21st century solution that covers the entire state, and now we're spending the rest of our time hoping to pull people into the 20th century in terms of surveying. And maybe in another 30 years we can pull them into the 21st century. The Corps of Engineers have been using our system to build the levees in New Orleans. We are, in fact, what we say the elevations are by state law. That's what it is. So it's there. Now the question is, do people want to use it? The problem is surveyors are too cheap and so it's difficult to sue them, to force them to change their ways, but I'm sure you'll find a way. Sorry. Subsidence has ruined the benchmarks. The benchmarks are established by surveys. Well, the problem is the land moves. In Plaquemines Parish, right after Katrina, we went down to Plaquemines Parish and gave the parish president the new elevations on all of the benchmarks in Plaquemines Parish. And I said, there's only one problem. These will all be bad again in about 3 months. We haven't been down there to fix it since. There are places, and I'll show you examples of this, but the bottom line in Plaquemines Parish is that half of the parish is about 2 feet lower than what reality is. Okay? Yes. No, it's what reality is. No, we're reality. This is what we think it is, what we know it is. When you go out, the maps, the FEMA flood maps and everything else, correct. And so all of these things are underestimating the risk. On the other hand, if you're in St. Tammany Parish, rejoice. It's actually somewhat higher. But FEMA does, that's another thing. How do we get credit for that? We showed the same thing in Cameron Parish. Well, when we started doing our studies, we went out and recalculated all of what the subsidence was, where we could, and what we showed is that the coastal parishes were subsiding at on average about half an inch per year. I mean, think about that, half an inch per year. You know, if you're living in Houma and you're living on Main Street, and Main Street is 10 feet above sea level, half an inch a year, vulnerability is not going to be good for you. It's going to be, storm surges will be able to come further inland than ever before. Unless you know about it, you can't do anything to fix it. Here is the footprint of the Mississippi River. This is the load. Remember I was talking about the diving board? Here you can actually see it. The subsidence gets less and less and less. The stars are actually uplift. And so here's an example where Louisiana has been dragging down the rest of the country. I think this is an example of that. But you also see some areas that are big spikes. This is over near Jennings. And this is due to, hey, guess what? Most of this over here is due to groundwater withdrawal. Rice farming. Big deal. You get up into here, it's pretty stable. Much of Louisiana is actually, in fact, much of Louisiana is actually rising. And we track this every day to see what's happening. Shreveport's going up at a whopping 2.3 millimeters per year. Seat belt up there almost. What you'll see is these are these shale plays that you find, Haynesville, Barnett Shale, things like that. Problem there is they require a huge amount of groundwater to do their work, and you might get local groundwater effects, but you're not going to see any major effects here. Here's when you do the geophysical modeling. This is some friends of mine at Caltech at JPL where we've done this. Here's Houma right here. This is, in fact, this is the area of greatest land loss. It's also the greatest area of thickness. It's the biggest load. It's not surprising. That's where we see most of the regional subsidence. Jet Propulsion Laboratory. The other thing is, when we look at it, this is a cross-section from Pensacola to Grand Isle of subsidence. We see this, and here's the footprint of the delta. We see this gentle rise here, or lessening of subsidence is this diving board. But then suddenly you get into New Orleans East, you get massive amounts of subsidence that can't be explained. So what's that due to? There's another process going on here. You get into New Orleans, you see the same thing. Where you want to live in Gretna. Gretna is actually rising. Why that would be, this is like Chalmette, it's like, no, only kid. But this is the reality. Kenner, moderate subsidence. You get down into Terrebonne and places like that, even more. So these are the processes causing subsidence. I divide them into shallow processes that occur above aquifers. Aquifers in New Orleans, they occur at about 700, about 500 to 700 feet, something like that. Natural compaction is very little, very little. The big deal is when you build a levee. You start pumping out the water so you can live there, the area subsides. This is what New Orleans subsidence mainly is about. You built the levees, you pump them out, the clays collapse, the ground goes down. This is human-induced. It causes various effects that I won't talk about right now. Deep processes, the loading, but this is relatively small in comparison. This is probably, this is about 10% of the problem. This is about 45% of the problem. But on the other hand, the biggest single factor outside of that is water pumping. In Houston, they've had like 12 feet of subsidence due to water pumping. In New Orleans, I think it's been probably several feet of local subsidence. There's other stuff that goes on. Oil and gas extraction. It doesn't work. Most of the reservoirs that we see in Louisiana are very deep. and you can't, the physics just don't work out. You can get some subsidence, maybe a couple of millimeters, but nothing more than that. It's nothing like groundwater, which is shallow. That's why, that's the difference. Shallow subsidence get a bigger effect. All right. Let's look at a little study that I've just completed that's taken me 2 years to write. It's the area from central New Orleans over to Biloxi. And what we did is we analyzed subsidence that we see at water gauges. Water gauges are all attached to big things like bridges. Those bridges are not sitting there dangling in the soil. These things are stuck into the ground as far as engineers can stick things into the ground to keep them stable, because they're afraid that the wind will blow the bridge over or that the bridge will actually sink, as we saw in the Green Bridge. Also, the only benchmarks, we also use benchmarks and looked at their behavior. And we only use benchmarks that were attached to long rods. And the reason for this, because we were testing the idea that, like most people think, that it's all due to changes that occur in this layer. This is a profile, a geological profile. This is the upper, here's the surface of the Earth, and there's a layer. This is things that, materials that were deposited during the last 10,000 years, what we call the Holocene. All of our samples went through this, so it has no effect of anything that we see here. Yet that's what most people think, that the subsidence is due to changes in here. And what we find is that's not what we find. Here are various, these are benchmarks. Every one of these is an individual benchmark. The different colors indicate different movements over different time intervals. And what you see is from Biloxi along the coast, there's not a lot of subsidence. You know, that's 5 centimeters. You're not seeing a lot, and then boom, the bottom drops out. When you get over into the industrialized areas, if you know where the NASA plant is, that's where it's happening, folks. And what goes on over there? God knows what they do. But they pump an enormous amount of industrial water, plus this happens right next to this power plant. I am available for expert work, incidentally. Here's one of the water gauges. This is over at the Wrigley's Pass, far away from any groundwater pumping. What we see there is relative sea level rise over the last 50 years of about 5.7 millimeters per year. In comparison, look at the Paris Road Bridge. Over here, this is about 40 millimeters per year. 40. Here's the subsidence derived from all of those water gauges. Look at how much of central New Orleans is more or less something like this. In fact, if we shoot this out even further, it's pretty much stable now, which is interesting because I think they've stopped a lot of the groundwater pumping that they were doing. On the other hand, this guy keeps going on like crazy. This is at the Paris Road Bridge. The Wrigley's, that's about, see how shallow that is? That's not affected by groundwater. This is groundwater effect. All right. Let's look at some of the other processes. Remember I was telling you about building levees. Well, this is the South Lafourche Levee District in this area right here. If you go down to Grand Isle, you drive down that road here. This is Golden Meadow, Galliano's up here, Cut Off is up here. But you notice that the colors, the magenta, the reddish colors are all below sea level. All of this is the open marsh out here. There's not a lot of it left over, but notice that it's above sea level. In here, a lot of it's below sea level. Building levees speeds up compaction. It speeds up the natural processes, just like in New Orleans. Notice up in here, See those very low numbers up in there? There's a minus 7 feet below sea level. That's in a place called Clovelly Farms. It's a cane field that was formed in the 30s. This is exactly what's happened in New Orleans. You go into a marshland, you build levees, you start pumping it out to keep it dry. It causes the land to sink. And it sinks at about 1.2 feet per decade. That's what we figure. And that'll be important in the last couple of slides when we talk about the future. In Houston, look at this. Look at the subsidence around Baytown. Boom. I mean, huge amounts of subsidence over time. We haven't told them. They're texting. Look at around. This is through Houston. This is the amount of subsidence in the 20th century per year. You got subsidence rates as high as 70 millimeters per year because of groundwater pumping. Talk about changing the hydrology of the area, talking about flood maps being screwed up. There you go. So what have we learned? Subsidence at any given point can be due to multiple causes. It's not just one thing. Subsidence has really been regarded as a one-dimensional thing. It's not one-dimensional, it's three-dimensional. It's four-dimensional. It changes with time. It's not going to be constant because of things that these processes are nonlinear, and if there's multiple ones going on, and if they're human-induced, you can guarantee they're not going to be. So trying to come up with some simplified idea is not going to work very well. Subsidence occurs well beyond the Mississippi River Delta. It's not just the wetlands. It's not just the Louisiana coast. It's a broad area that is affected. So in order to do this properly, you got to measure it right. Let me get down to predicting the future. No. Okay. Right. Yep. Yes. They're in clays, and the water absorbs the clays. Then you start pumping it out, and the clays collapse. The problem is they're plastic. They can't spring back. In other areas, in sandier areas, you can pump the water out, and you can pump it back in, and the land will go up. Okay. So predicting, we're going to the fool's paradise. That's our destination. Predicting if I could predict the future, I'd be in Vegas. I wouldn't be here. What we're going to do is our simple model for future subsidence is really a lower bound. Here are all of the things that can cause it, but we're only going to take the things that we know are going to happen. We're only going to take things like natural consolidation, compaction in a few areas. We're going to take areas that are leveed. We're going to take Morganza of the Gulf. I'm sure you've heard of Morganza of the Gulf and Donaldsonville of the Gulf. These are things that are going to be built or in the process of being built. We're going to look at see what happens. Let me just tell you, anybody from Homa or that or Terrebonne, if I tell this to the people there all the time, hell, if I lived in Homa, I'd want a levee. I know it's going to subside, but you're dead meat without a levee in front of you in South Louisiana. You are in big trouble without one. But that's the price you're going to pay. You got to pay. We're also going to look at sediment loads due to this flexure. That's not going to stop. We're subsiding due to loads that were put onto the Louisiana coast 1,000 years ago. But it takes time for nature to deal with it. It's not going to stop. We're not going to worry about faulting. Faulting occurs. Faulting may be very significant for very short periods of time, causing big time problems. But I can't predict when we're going to have a fault, an earthquake. Water pumping. I just showed you that water pumping is huge. But I can't predict. Water pumping is something that people decide. I cannot predict what people are going to decide. So this is a lower bound. Oil and gas extraction. It's not going to be big, but, you know.
We're talking about water pocket that comes there.
Yes.
As opposed to water.
Correct. Correct. So what we're going to do, is we're going to look at areas that are behind levees, and we're going to see that we're basically going to say that those areas that are in the wetlands are going to subside, like the empirical observations. Remember I said 1.2 feet per decade. So we're going to apply those numbers to areas behind levees. I know that these things, we're going to apply them linearly, but we know that consolidation curves are exponential, but we're going to do it anyway, because we're heading for the fool's paradise. So we're also going to we're going to start with a digital elevation model of today, and then we're going to project it, and we're going to subtract the amount of subsidence from each area through time. And we're going to look at the effects of building levees. Also, we're going to look at areas outside and see how they fare. But we also cannot predict what people are going to do. If we're going to start dumping all kinds of dredge, pipelines and sediments, building up the land, we can't put that in here because I don't know what it is. So this is just to give you an educated idea of what could be happening. Well, here's the subsidence due to the tectonic loading, and you can see through here. Here's Vermilion Bay, Cocodrie. This is Terrebonne Parish. New Orleans is over here. And we see that in this area here, it's going to be about 6-7 millimeters a year, plus sea level rise, which right now gets you to about 9. 9 is what the tide gauge at Grand Isle tells us right now. So that's pretty good agreement. We're also here the planned and existing hurricane protection systems. We see in yellow are the existing ones. Here's Morganza to the Gulf. Here's Donaldsonville to the Gulf in orange. We're going to put all those things in, and then we're basically going to say, apply some numbers to those to look at things. The areas behind levees that are in wetland areas, we call those constrained levees, and these are areas where there's going to be an abnormal amount of subsidence going on due to this. Okay, you can pick a parish to watch what happens. In this color blue, this is the percent of land that lie below sea level, parish by parish, through 2100. This is what we have today. Orleans Parish has 54% of its land lies below sea level. Jefferson, 34%, and you can see that. By 2050, it's the darker blue, and you can see that Orleans is now going to be up to 73%, because it's going to continue to subside. And this is taking a very ultra-conservative view of sea level rise. If we add some of these hockey stick changes that we might see, that's going to change. It may shove everything over to 100%. Okay. Here is the areas of magenta are areas that are below sea level in the coast. Areas, you see New Orleans, everybody knows about the bowl over here. Did you know there's a bowl in Morgan City? Below sea level. Most of South Lafourche Levee District is below sea level. All of these areas where you've impounded waters, even roads, out in this area here, you get areas that are below sea level because somebody has built a small little potato levee just to keep water from coming in. And that's what a hypsometric curve, I'll ignore those for right now. So right now we see about 8.9% of the area is below sea level in South Louisiana. You know, if it wasn't for the levees, they'd be what? Lakes. Well, here's what it's going to look like in 2050. We're now up to 15.5%, and you can see that large expanses of areas that are now behind the protection of the Morganza of the Gulf are now below sea level.
The stakes that are in front of the levees are just going to be gone.
They're going to be gone. That's right. And I mean, it'll just be open water. But again, what's sea level going to do? You look at, here's the front of this, of the, the mouth of the Mississippi River South Pass, all the passes here. They're not going to be able to keep up. The marsh can't grow fast enough to maintain itself. And so, plus, the other thing is, who knows how many hurricanes are going to hit this area and how much erosion is going to occur? What is going to happen climatically? This is a lower bound, folks, lower bound. 2100. This is what your coast is going to look like. The coast is basically going to be the levees left standing. Now, what you do out here, if you want to go out here and do coastal restoration to buffer the coast, if you believe in that, I mean, you can do that. But it's a matter of, this is what you're starting with. Now the question is, we're going to have all of this money, what should we spend it on? You should send everybody to Harvard in Louisiana. I don't know if that would help. So here's what it's going to turn out to be in the future. It's not pretty. It's worse than what this is. This is the minimum. Oh. Mr. Bill, you were asking me about Mr. Go. Here is the operational official storm surge model it was created by National Oceanographic and Atmospheric Administration. Here is using the existing topography. This was done during Hurricane Katrina, and what it showed was no. This is the pre-existing elevation data. As it turns out, it's not data. They used authorized elevations. In other words, this was what it was supposed to be if they had the levees up high enough, but they didn't do it because the subsidence had caused them to subside, plus the benchmarks were off, so they built them too low to start with. Here is the funnel. You've all heard of the infamous funnel right there. Here's evil Mr. Go over here. You can see it. And here's the funnel. And the unsuspecting folks of New Orleans were affected by this engineering disaster. Well, we came back, and I started looking at this stuff, and I wondered, God, is this really true? So the state asked us to go and measure all of the hurricane protection levee systems in southeast Louisiana. We went out there. It took us about 3 months to run around and do that. Well, what we found was, and notice these are little tide gauge flags. See them? It shows that Chalmette only flooded to about 7 to 8 feet. Some places, last time I looked, there were, roofs that were underwater. It was somewhat higher than that in many places. Notice that these models, all the models, showed what? That New Orleans was going to flood. That it flooded. This is flooded area in here. This is New Orleans East. That supposedly didn't flood. But these models show that they did flood. Well, they didn't. This part, Metairie or Kenner didn't flood. Why the flood wall broke on the 17th Canal on this side and not that side is still of some question. Fact is, these were not built properly, and they were not able to take the pressures. But here is where we ran the model again using the correct elevations, and what do you find? There's no funnel. Because the levee, Mr. Go was not high enough. The water just came right over, and there are movies to prove it. On the other hand, you guys don't know any federal judges, do you? Please. Well, the fact is, Mr. Go had no effect. It may have done that early on, but as soon as the water got high enough, it went right over the top, and it flooded all of this area here, and there was no funnel. So there's a lot of other things to talk about if you want to talk about a lot of the other things that people have very strong beliefs about, that wetlands form barriers. They're the buffer. Can we build? I remember asking these people who are the physicists that build these models, and I asked them, do wetlands provide storm surge protection? And what they say is no. Only in very small storms. However, you get to a category 2, 3, 4, 5, forget it. You'd have to. I said, how big would the wetlands have to be? And they said, well, you'd have to build it to Cuba. The fact is, wetlands don't have that effect. On the other hand, their effect becomes greater. In other words, if you had a massive coastal forest out here of cypress, that's a totally different story. You would have elevation, and it would be sustainable and everything else. But if you've ever run around the coast, what do you find? These death forests. Forests that are they're all dead because of saltwater intrusion. Saltwater intrusion basically says the ocean is moving landwards and replacing fresh water with salt water, and if you're not ready for that, you will die.
Are you insinuating that our coastal forests are built on saltwater intrusion, or was it the law? I mean, they were gone before.
Oh yeah, there's. Well, sure. There's no question that there's been land use practices here that are just not that don't comport well with this area here. But there certainly are areas of forests in some areas. You see over into the Maurepas Basin area, for instance, tremendous amount of logging. But on the other hand, you see the forest dying today because of the change in the ecosystem. Seasonal is part of it. Needs to have seasonal flooding.
Which
right.
is precisely my point. That if we were allowed to have flooding now, we can still have coast to
if there was a way of, again, it's the saltwater intrusion, and they're coming into these areas. What people are now doing over in this area here, they're saying, hey, let's build some more barriers over here and put some pumps in to lower the water. Well, what's gonna happen? You're gonna get the unintended consequence of, in other words, this is your fix will not fix it. Something else will then go wrong. Absolutely.
And so that, before we even get to this, man's been the big agent. The reality is that historic times the Delta has grown and then receded all the way up, halfway up to St. Louis at one point or another, depending on the relative land and ocean level. What we are seeing in the Mississippi coast is we were already significantly receding before man set foot in this area. Chandeliers in the old coast that were receding from. So I want to keep that perspective in this too. It might be we still be receiving, still be paid?
No, in fact, if you go back out offshore of Vermilion, that area in there, there's a place called Ship Shoals. What is Ship Shoals? It's a bunch of sand that's sitting there. It's the future of what the Chandelier Islands are going to look like in another several hundred years. Okay? What you see, if you know where to look, you'll see the various stages of development of the delta. You see the areas, you see the Wax Lake, Atchafalaya Delta area. Okay? Oh, it's building land. Yes, true. You shut that off, and it will then continue to subside, go below sea level. Waves will get at it, winnow away all of the fine material, leaving behind the Chandelier Islands type materials. And so you see this evolution played out. The bottom line is this is a very dynamic area. The problem is flooding is an essential part of maintaining the elevation. And elevation is, as someone likes to keep saying, is elevation is our salvation from inundation. The fact is, how do you live on land like this? That's really the question. My answer is you need to live like people that originally lived here. You need to live, you need to have houseboats. You need to have, you can't put a Walmart into the wetlands or a strip mall. Yeah, that's the answer.
So I guess the two of the main points that I've heard is that as part of several, but one is that there are effects that are things that are happening that are far beyond human control, that were happening before, that are going to happen, that are outside of it. Basically, nature's a lot bigger than this.
That's right.
But there's also, which I readily accept, there's also a component of this that at several points, human intervention has caused serious problems. It's set into motion change events that has seriously exacerbated what we're doing.
That's right.
If we take out that component, I guess preliminary question is where are we? If we take out the screw ups that we've done post 1927, where are we? How sustainable is our faith?
Well, maybe we should add in, I mean, if we're talking about, what about global issues? I mean, if you want to really, I mean, I think that discussion should be expansive. Now, I think if you start getting into that discussion, the minds are open, and then you can begin to think about how can we design a place in Louisiana for people to live and to do various things and whatever. I think obviously the people that should be living on the coast are the people, if there's a need to live there. If you're a shrimper or a oyster person or whatever, you need to be near the water. You can't live in Washington Parish. And so the question then becomes, once we understand what we're up against, now we can begin to use ideas to find areas that are less vulnerable, that are more sustainable, and then begin to think about it in that sort of way, and then to think about, obviously one of the things that you could do, you go over here and you blow up the river at Donaldsonville, and you let nature do it. It's free. It's a couple $100 worth of C4, and you can do that. And nature will do its thing. It will be on time. It'll be sustainable. Nature will show that. However, I think the real issue is how do we transition to the inevitable? And that's perhaps the point that you're trying to make in this course. How do we transition to the inevitable?
The second part is
You can't answer that question. That's a legal question.
My counsel has advised me.
That's what we're going to have to figure out in class. That's our job. How to get folks off the coast.
lot in the last 40 years, last 10 years a lot. Is there any merit to attempting to reverse our screw-up in wetland policy, in navigation policy? Is there any reason to do that? I think Professor Richards would say no, move. And I think, and I'm not saying that's wrong or right, is there any merit towards trying to take away some of the aggravating factors that we have undoubtedly put into this decision?
I absolutely. It may sound like I'm the guy running around dumping the glasses over and dumping the water out, but it's not. It's one in which it comes back to the original question. I said, restore to what? Okay, that is a community question. That is for all of us to look at. What are we trying to accomplish? Are we trying to accomplish an area that will be here forever? That will defy anything that nature tries to do? Or is it, what do we want this land to be? It's pretty obvious to me. I will say one thing that will control everything. As soon as the Gulf of Mexico oil is played out, probably in a couple hundred years, there's a lot of oil here. Money is to be made, and people will be here to make money. The day that they can't make money off of oil, the rest of the country is going to say, you're on your own. And then I don't think you have the resources to do that. So the question should be is, I think we owe it to, I think we have places where there's culture, there's population. I think we owe it to perhaps do heroic things in those areas for some time. I think we should perhaps try to do no harm. I think we should try to do some of the other things. However, knowing, let us not fool ourselves into thinking that we're going to restore the wetlands for hurricane protection. Let us restore the wetlands for the wetlands. The wetlands are worth saving all by themselves. But let's not, hurricane protection, I mean, after Katrina, I made, I made some suggestions to some people about what you could do, how you might, I think in New Orleans, I think they made a big mistake by not reducing the footprint of the city. Huge. I think in doing so, you could have said, look, we realize our risk. We're going to now reduce. We're going to reduce our vulnerability by pulling in our horns a little bit. However, in doing so, we're going to make this a more livable city. We're going to make it a more, we should have been doing more of these things. We should have